So hello everyone. So in this video I'm going to talk about the concept of linear regression. During my teaching years, the last couple of years, I have realized that in all levels, I taught research method in bachelor, masters and PhD in all levels. The simple regression, how it works, we think that we understand it, but still I see that many of us do not really understand how it works. Okay. So that's why I decided to make this video on the concept of linear regression, going through the basic and key terms. Okay. So here you can see my setup here in the Excel, and actually the way I will do it, it will be more or less similar to doing it by hand. Okay, I will follow a very analog approach. Okay, you can of course do these regressions very easily with SPSS or Stata in other softwares, or even in Excel you can do it very easily. But still, you need to understand what is going on when you estimate a regression, when you just click there and get this coefficient. So you have to understand what's really going on the back end. Okay, so that's the idea of this video, that I want to show you what's going on at the back end. So for simplicity, I'm considering here a very small data set, only two variables, x and y, and only 6 observations. Okay, so here by x I indicate advertising expense in $1 million maybe, and by y I indicate sales in $1 million maybe. So these are hypothetical numbers. Okay, so normally you will have some observed data. Okay, so now I will proceed with these two and I will show you how regression works. And here I have a list of relevant equations. So first of all, this is my regression expression: y equals to alpha plus beta x and then error term. Okay, so here y represents the dependent variable cells, alpha is the intercept, which is the fixed value of y, the dependent variable, regardless of the value of x, and then we have beta, which indicates the association between the value variable x and y, and x is the observed value of the variable x, and then e is the error term, the portion of value of y which is not explained by values of x. Okay, so when what actually we are trying to do is that we are trying to explain all the values of y here with the values of x, and how we know that we cannot explain them exactly 100%, but that's what we want to see, how much we can explain them. Okay, and normally the percentage explanation that we actually get from the R square in the end of the regression, we get it from there. But anyway, so to get here, to do the regression estimation, we will need these values: alpha, beta, and some error term also, but error is not very important at the moment, but mostly alpha and beta. Okay, here you see the equation for beta: summation of xi minus x bar multiplied with yi minus y bar divided by the summation of x minus xi minus x bar whole square. So the value of beta will be actually kind of enough for us to calculate the regression equation, but sometimes we may still be interested in knowing the correlation, and to know the correlation we will need covariance between x and y divided by the standard deviation of x and y and their multiplication. Okay, and for covariance we will need the multiplication of x I minus x bar with yi minus y bar. Okay, and their summation, if you see this value here and this value here is more or less the same. So that's the benefit. If I calculate the covariance in the beginning, then actually I can just plot the value here directly. Before we go to covariance, actually we may also like to see the standard deviation. Okay, standard deviation is normally a measure of dispersion in data, and here if I calculate this value, we see that this we can directly plot here. Okay, so this could be useful here as well. So let's go through all of them one by one. First, what I will do is I will calculate the mean here. Okay, so here we just take the average of all the values. I will just use the command average. This is very simple, so that's why I'm not doing it manually here. So the mean of x is 9 and mean of y is 17. So here if we look here to calculate standard deviation, we will need what will we need? We will need xi minus x bar square, right? So xi means each of the values of x, and x bar means the mean. Okay, so let's say we create one cell here, xi minus x bar. Okay, so I'm missing the symbol here, but that's what I mean. To do that, I will just use the equal to function, and then I will select this one minus the mean of x, and I will fix it. I will use the F4 button to fix it. Okay, so I'm fixing it, and then I will just drag it down here. So similarly, we can calculate this manually as well, right? So here now I get the value of this part, xi minus x bar. But now we also want their square and sum it up. Okay, so now let's say I just copy this, paste it here, and I will take the square of it. So to do the square, I will just select this one, use the square symbol and square equal to, and we get the square. Okay, we will also need the sum here as represented by the symbol here. We will need the sum. So to do the sum, just add it up. So sum, and then I'm adding it up here. Okay, so we should do the same thing for y as well. Okay, so let's say y I minus y bar. I'm missing the bar symbol here. Okay, so to do that, again, what I will press equal to, then I will press y minus the mean, and then I will again press F4 to fix this mean, because I'll be using the same cell for whenever I'm subtracting from y, I'm using the same cell. That's why I fixed it to the mean. Okay, and again here, then we want to make the square of it again. Okay, equal to this square this. Then again I want to take the sum. Okay, so from here actually we can calculate the standard deviation if we want. How do we do that? We can have the standard deviation of x, and we can also calculate the standard deviation of y. So let's say I'm calculating it here. We have the value here, we have to do a square root of it. Okay, so we use the command square root of this value when dividing it by n minus 1. Here our n is 6, so n minus 1 is 5. Okay, so that's how we get the standard deviation here. Similarly, we could actually get it by using the Excel command, but I wanted to show the calculation. Okay, so how we get it. So then again we can do the same thing for y, right? Divided by n minus 1, 5, and then bracket close. Okay, so we get the same standard deviation for y, right? So here if you look, actually what we're doing is, when we calculate the standard deviation, we just want to see the dispersion from the mean, because we are always subtracting the mean from each of the values of our variable. So actually we are getting a general idea of how the data is dispersed from the mean. Okay, so now let's say we go to covariance calculation. So here now our life will be much easier. We see that we have to multiply xi minus x bar with yi minus y bar. We have both the cells here, right? This one and this one. So we just need to multiply them. So I will just copy them here. So here we have the multiplication form, and here I will do the multiplication. This one multiplied with this one. Okay, So we have them here, and then here I will have the sum command. So I will just add it up, all of it, right? So now the covariance is this value divided by n minus 1. Okay, so now the covariance is for actually both of them. Covariance cannot be calculated for one of the variables, so it's actually for both of them here. So here this value will be this divided by n minus 1, that means 5 again, so the covariance is 9.6. Covariance actually cannot tell us much about the strength of the relationship between the two variables. Covariance can tell us only the direction of the relationship. So for instance, from positive value here, we can see that there is a positive relationship with x and y here in this case. Okay, but how strong is the relationship, we cannot really find it from here. To see that, we will need to calculate correlation, okay, which is represented by R. Okay, so here to calculate the value of R, again it will be one value. Actually this will be small r, or I will just write core. I'll just write core. Okay, so here I merged both the cells again because we will get only one value for both the variables. Here it's very simple. Here we just have to divide the correlation by the multiplication of standard deviation of both the variables. Okay, so that's it, we get a correlation here. So here we see the correlation is 0.878, which is actually quite high. The value of correlation can be between 0 and 1. Actually, yeah, -1, 2 plus 1, and in the middle we have 0, right? So this is the range for correlation. Negative values means negative correlation, positive values mean positive correlation. Okay, negative correlation means that when one variable increases, another variable decreases, value of another variable decreases. Positive correlation means that with one variable increases, another variable also increases. For instance, here we have a positive correlation, right? So when the values of x increases, that means when we invest more on advertising expense, our sales will also increase. Okay, that's what we get from here. And normally 0 means no association between the two variables. A correlation value of 0 means no association between the two variables. So up to 0.30 means a mild association. From 0.5 we have a moderate association. 0.7 we have more or less very good association, and above 0.8 or 0.9 is very strong association. Okay, so now let's move here with the beta. Now can we calculate the beta here? We actually can do it very easily. Okay, so here again we will get only one value for beta. Just quickly clean this. So here for the beta, we see the summation of the multiplication of these two, which we have here 48. We divide it with the first one, with the summation of the multiplication with the xi minus x bar square summation of the first variable x, the independent variable. Okay, so that's what we get here, the beta value. Okay, so now we get the beta value here. We have the beta values here. Now can we calculate alpha? Yes, actually we can do it rather easily. Okay, so here how do we calculate alpha? It turns out that when we talk about a linear regression, then the regression line will always go through the mean of x and y. Okay, so the mean of x and y. So using these two values and the beta, we can actually calculate the value of alpha. So to do that, we use we just plot the information we have in hand in this equation. Okay, how do we do it? Like y equals to, let's say y equals to 17 right? And then we have alpha. The value of alpha we do not know, okay? Plus we have beta. Beta is 1.4, right? 1.41, I'm just using 1.4, multiplied with value of x, which will be 9 here, okay? And we can ignore the error term part, because error term is the part which is not explained by the value of x, okay, by the independent variable, so we can just ignore that. So now if we do the calculation here, we will get that the value of alpha, if we just do the simple mathematics here, you will get the value of alpha is 4.29, okay? So you will simply get the value of alpha is 4.29. So let's note it down. Okay. So actually now for any value of x, we can calculate the value of y. So these are our main regression coefficients, okay? So now here the beta is the coefficient of x, okay, or it is also known as the parameter. So for each unit increase in x, the value of y will increase by 1.41, okay? So that's the rate of change in y due to change in 1 unit change in x. This is also known as the slope, okay? And then we have the alpha. Alpha is the constant here, right? Regardless of the values of x, we will have cells of 4.29. Okay, that's it. It would be a bit more clear if I just plot it. Let's say I just plot it here, select them, I go to insert, I go to a scatter plot, and I plot it here. Both the values of x and y, I just plot them here. Okay, can try to make it look fancier like this. This is the plot of x and y, okay? And we say that a regression line, if we try to feed a regression line to this data, we say that the regression line always go through the mean of x and y of our independent variables. So here x is 9 and y is 17, the mean, right? So it will be 9 and here it will be 17, right? It will actually go through this point, okay? So the regression line would look something like this. And do we know the starting point? The starting point will be, what will be the starting point? The starting point is the alpha, okay? That's our constant. So alpha is, the starting point of the regression line is 4.29. So I'm assuming 4.29 is just below 5, okay? So now, do you wonder like why the regression always starts from some point above 0 but not directly at 0? Why is it? One reason is that, you know, in real life, if you have some product in a market, regardless of if you're doing some ad or not, you will have some cells. It is very unlikely that you will have 0 cells, okay? Or if you just think about any other relationship, let's say if we think about the dependent variable exam score and the independent variable study hours, okay? So let's say you just sit for the exam. You haven't studied at all. You just sat for the exam. And regardless of the fact that you haven't studied, you will still score something. Maybe you will not pass, but still you will score something. You will not score 0, right? So that's why the value of regression line always starts from some point above 0, okay? And this beta is the value for 1 unit increase from this point, how much the value of y will increase, okay? So let's say if I draw a line here, oops, it should be a straight line, okay? So this part is the beta, okay? This part is the beta. When the value increased from 0 to 1, the value of y increased 1.4. When the value increased from 1 to 2, the value increased 2 multiplied with 1.41. That is like with 4.2 the constant, we will add something like 2.8. So we multiplied 2 with beta 6, 7. Okay, so we will get a value close to 7 here. When we have 2 here, we will have a value close to 7, as you can see, right? So this is how it works. For 1 unit increase in the value of independent variable, the value of dependent variable increases by beta, and alpha is the constant. Regardless of the value of independent variable, this will be the value of dependent variable. Okay, so now we have this, but some more things comes up here. So normally after doing the regression, we will come across some values like r square. Okay, so here I have the equation for r square. Here we have SSR divided by SSE plus SSR. Okay, so SSR is known as sum squares of regression, and SSE is known as sum squares of error. And when we add these two, SST is called total sum of squares. So this is the portion that is explained by the regression, right? So how much is explained out of the total variance? Okay, so that's what we get from r square, and that's what we call the percentage explained by the by the value of r square. So normally if we get a value of r square value of like 0.7 in regression model, you'd say that all the independent variables explains 70% change in the dependent variable. Okay, so that's how we explain the r square. But this SSR, this is known as the sum of regression, right? So what is the sum of regression? So now let's say first what I will do is I will draw two lines with the means of x and y. Okay, so mean of x is 9. For that the line will go through here, as we know that it will go through this point. For mean of y, we will have this line here, which 17, which will go here. Okay, so as we said before, the regression line must go through this point, 9 and 17, and of course it is going through this point, right? So now the SSR, okay, now the SSR, which is the sum of squares of the regression, which means the distance from the regression line, as we can see here, which means the distance from the regression from predicted values and the mean of y. Okay, so this line, the regression line, represents normally the predicted values y cap. Okay, here this line represents mean of y. Okay, and this line is mean of x. Okay, so now SSR is the difference from the regression line to the mean of y. Okay, so that's the SSR. Okay, I can try to write it here, SSR. Then we have SSE, as we can see here. We have SSE, which is the difference from the observed values of y to the predicted value, right? This part, okay? Observed value to the predicted value, which represents the error terms actually, okay? And we take the square of it and then we sum it. That's why it is called the sum of squares of error. Okay, so these are here. So these are the SSE. And then when we add all of them, then we call it SST. When we add up SSR and SSE, then we call them SSE. But also this is the difference from the yi, from all the observed values to the mean of y. Okay, so it is also the difference here, this difference, the total difference is also the difference from the observed values to the mean of y. Okay, this is the SST. We square them for all of them and then we sum it up. So here we have the equations to calculate SSR, SSE and SST. And also we have the equation to calculate r square based on these values, and then we can also calculate the adjusted r square and the F statistics that we normally get in SPSS, right? So to do all these things, let's calculate this one first. Okay, the predicted value of y minus y mean square. How do we calculate it? What is the predicted value? Here you see that we have a hat, not bar. The bar means the mean value of y, the average. And here this means the predicted value. Okay, the hat means the predicted value. But what is the predicted value of y? Here we will calculate the predicted value of y. Okay. So let's say I'm using this symbol to indicate y hat. Okay. So now what will be the predicted value of y? We will just plot all the values here. So we will have alpha plus, we have beta, we have the beta. Beta is then multiplied with the values of x, right? Values of x is here, and then we will ignore the error term because term is not explained by the model here. So the portion is not explained, is not covered in the error term, right? Error term is the distance between predicted value and the real values of y. That's the error term, right? And just because we will be using these values as fixed value when calculating all of them, all the values here, so I will just put F4 here to fix this, and also then to fix this one. Okay, these two are fixed, and this will change when we click down. This will change here, right? So let's say I just clicked it here. So these are the predicted values of y based on the given data, given regression model, right? So that's what we could calculate easily. So now let's say if you want to see the error term is simply the difference between this minus the real values. Okay, these are the error terms. These are the portion that is not explained by the regression model. Okay, but anyway, for SSR what we need is this part, y predicted minus y bar square and their sum, right? So I will just create one new column here. Actually I think I will need more than one, so I will just click create 3 of them. So let's say first we calculate SSR, which is, so we will minus y hat. So we will have y hat minus y bar, and then we will have the square of that, right? So that's what we want to calculate here. So let's say I start with equal. So the value of y hat, we have the value of y hat here. We deduct the mean of y, which is here. Okay, and then I will do the square here at the same time, because otherwise I have to create more cells here, which I don't want to. And also we should not forget to fix this value here, because I'll be using the same mean for all the cells, right? And then also I have to put the square here, right? And then if I just drag it, I get the value here. I get the SSR. It's not the SSR, but the SSR will be simply the sum of it. Okay, so if I just take the sum of it, then I have the SSR, right? This is my value of SSR. Similarly, I can calculate SSE, which is yi minus y hat. Okay, and we take the sum of that. So if I just do that, we have yi minus, we have y hat, and then we take the square of that, right? So let's say I start the first bracket. I have to first select yi, which is here the value of y. Yi means the value of y, minus the y hat, the value of y hat here, right? And now we do not have to fix anything because both the values will be changing, right? So we don't have to fix. And then just scroll it down, and then if we just take the sum of it, we get this value. This is the value of SSE, right? So just write it down here. This one is SSR. If we sum it up, we get 88, right? So 88 should be the value of SSR, SST. 88 should be the value of SST, right? The total sum of squares, right? But we also say that this equation will give us the same value, but just to double check, let's do this and just see if we get the same. So here again I will use yi minus, I will use y bar, and then I will square it, right? So I'm starting a function here equal to first bracket, yi is here the values of y, the original values of y, yi minus, we will have the values of y bar here, right? We'll have the values of y bar, which is here. We have the mean value of y, and now y bar is one value, so we have to fix it. I'm pressing F4 to fix it, and then I close, and then I put the square here, okay, and then enter. Then I will just drag it down to get all the values, right? Do we have the sum 88? Yes, we have the sum 88. So you see both ways it gives us the same value, right? Both ways it gives us the same value, okay? So now here the value of r square, the value of r square would be simply we divide the SSR by, we divide it by SST, total sum of squares, right? This will be our value of r square. So what does that mean? That means that the variable x explains 77% variation in the variable y, okay? So the independent variable x explains 77% variation of changes in the dependent variable y, okay? So we could calculate actually the r square from here, right? So we just plot the values in this equation and we get the values of r square. But now do you want to calculate the adjusted r square? Sometimes we do that, right? Adjusted r square is actually nothing but when we control for the sample size. This r square here, we do not control for the sample size, but when we control for the sample size, that's when we get the adjusted r square, okay? Okay, let's do that. Let's do the calculation. So here, let's say we say adj r square. So here we will go for equal to, and then we have 1, right? 1, then minus, we start another bracket, 1 minus r square, the value of r square, we select it, then we have the multiplication here, multiply with n minus 1. So we have n of 6, n minus 1 is 5, right? 5 divided by n minus k minus 1. N is the sample size, k is the number of independent variables, and then minus 1. So we have 6 observation minus, we have only one independent variable, so 6 minus 1 is 5, and then minus 1 is 4, so we divide it by 4, okay? So this is our adjusted r square, okay? So normally if the difference between the r square and adjusted r square is too big, that means that the model is not robust, but here the difference is not very high, okay? So this is okay. And then similarly we can also calculate the value of F-statistic, okay? Normally in a regression model, based on the value of f, we normally conclude if there are some significant effects or not, right? In general, like for the overall model, we will have F-statistic, right? So let's calculate that, and as you see, it's also very easy, right? So let's say we to calculate this, we start with equal to the value of r square. I will start a bracket. So first I will start a bracket, and then I will click the value of r square, first one, that is divided by 1 minus r square, right? Another bracket, 1 minus r square, close them. I close both the brackets. Then we multiply this with n minus k minus 1. So again, n is 6, minus k is 1, one independent variable, so n minus 6 minus 1 is 5, minus 1 is 4, so we have 4 divided by k is 1, so that's it. So that's how we can calculate the value of F-statistic as well. And normally F-statistic also has a distribution like a t-distribution, okay? Normally it is distribution. When we will have a value of 1.96, normally we will say that there is a significant effect. But for F-statistic, the value is close to 4. The exact value is 3.95. So when we have the value of higher than 3.95, then means that there is significant effect. So this regression model is a statistically significant model. The effect of X on Y is significant. Okay, so that's all about it. So thank you for watching the video, and if you like it, please hit the subscribe button, and don't forget to share with your friends and colleagues.